In this video, we look at a topic that in and of itself is a entire field of mathematics called differential equations, and it's actually very useful in physics and many of the applied mathematical fields probably use differential equations, modeling, those type of things. So a differential equation is just an equation that involves derivatives. And the big distinction between that type of equation and ones that you've solved probably so far in your mathematical career is that equations like linear equations, quadratic equation, exponential, the solution to those equations are numbers, right? The solution to a differential equation is a function. All right, so it's a function that satisfies the given equation. Couple of terms. The order of the differential equation is just the highest derivative it contains. So if you look at this example here, this would be a second order differential equation. And in calculus, you usually don't spend a lot of time solving second order differential equations, usually just first order. But to give you an idea of what a differential equation is, I'm gonna take a look at this equation here. That's a differential equation. Basically, it's saying what function, such that when you take its second derivative and then add it to itself, gives you 0. So there are techniques to finding such a function, but what we need to do here is just to test to see if this actually is a solution. So the way we do that is we find the second derivative of this guy, add it to itself, and see if we get 0. So first we got to find the first derivative, and that's negative 3 sine of x plus 5 cosine of x. And so therefore the second derivative is going to be negative 3 cosine of x minus 5 sine of x. So now let's actually let's plug these in. So I'm going to take this, plug it in here. I'm going to take y, plug it in here, and see if I get 0. So let's see, negative 3 cosine of x minus 5 sine of x plus 3 cosine of x plus 5 sine of x, and that does indeed get you 0. So the answer to this question is yes. We'll say this is a solution. This is a solution. All right, now you'll notice one thing, as I said, it is a solution. I didn't say it's the solution. You'll find that the solution to a differential equation is not just one function, it's usually a whole family of functions. In many cases, if you're looking for a specific function, you can find that. But the solution to a differential equation is often, broadly speaking, a whole family of functions. So we'll take a look at solving differential equations and finding what are called general and general and particular solutions. Here I actually want to solve a differential equation, dy dx equals 2y, using a technique called separation of variables. But before I do that, I want to do what's called an example of a slope field. So this grid right here is we're going to use it to draw what's called a slope field. And the way the slope field works is that your derivative is going to give you the slope of your function at any point, or family of functions at any point. And so what we're going to do is, by plugging in certain values into our derivative, we can kind of get a short glimpse of the linearization at that instant, and we're going to make a little indication of that slope. And when you look at the slope field, you'll see that it captures the entire family of functions who have this derivative. So I'll just talk about that a little bit here. This says that dy dx equals 2y. So let's just we'll plug in a few points and then we'll look for patterns. First of all, let's say, what would dy dx be at the point 0, 0? Well, since the derivative is only in terms of the y coordinate, that just means plug 0 in for y. So it would be 2 times 0, which is 0. So a slope of 0 is horizontal. So I'm going to go up here where right at the origin, 0, 0. And I'm just going to make a quick indication of a horizontal tangent line right there. Now, one thing you may notice is that that was 0, 0, but all that was important was that the y coordinate was 0. So any point on this grid where the y coordinate is 0, that's going to have a slope of 0. So that's all along the x-axis. All right. So now let's plug in 0, 1. So dy dx at the point 0, 1. Well, that would be 2 times the y coordinate according to that differential equation up there. So that's 2 times 1, which is 2. So now I go to the point 0, 1 and indicate a slope of 2, which would be roughly something like that. All right, now it doesn't have to be perfect, but that's good enough. Now every point on that horizontal line, every point on the line y equals 1 is going to have a slope of 2. So I can just copy that and sort of make all these slopes parallel. All right, we can plug in. So you can see what I'm doing here. I'm taking some information. I'm getting information about the derivative at certain points, and what we'll see is what's called a slope field. Let's do 2, 0, 0, 2. So that gives me 2 times 2, which is 4. And that would just be even steeper than this guy. Okay, it can be difficult to indicate, but as long as you're getting, at the end of the day, it's almost like one of those Monet paintings where the details might be a little off when you look close up, but when you step back, you should get a good sense of the pattern. Now here, so this was y equals 1, y equals 2, y equals 0. At this point, I think we get the idea that the derivative is just in terms of the y coordinate. The y coordinate here is -1, so I need to indicate a slope of -1. Sorry, -2, because when I plug in -1, I get 2 times -2. So that should be something like this. These are my slopes of -2. And then here, when I plug in -2 for y, I get slopes of -4. All right. So this here is called a slope field. And each differential equation comes with a slope field. And the idea now is when we solve this differential equation, we should recognize that the solution is going to, its graph is going to be captured by this slope field. All right. So this slope field represents a family of functions whose derivative is 2y. So now let's actually solve this differential equation. So we're going to find find the general solution. To this differential equation. And so that involves a technique called separation of variables. We've seen earlier when we were studying differentials that the dy and the dx can conveniently at times be separated and viewed as variables themselves. So I'm going to separate the variables by first putting the 2y, or actually I'm going to put the y below the dy and the dx with the 2. So all I did was divide both sides of this equation up here by y and times both sides by dx. Now what we're going to do is we're going to do what's called taking the antiderivative. We're going to take the antiderivative of both sides. So in this case, antidifferentiation is like an operation. You can do it to both sides and retain the validity of the equation. So the right side's easy. The antiderivative of 2 with respect to x is just 2x plus the constant c, because there are many functions whose derivative is 2x. I'm sorry, is 2. They all differ by a constant. The antiderivative of 1 over y, which is essentially what this is, that is the natural log of the absolute value of y. Now, you don't need to put a plus c here, because if you put a plus c on the left and there's a plus c on the right, you could always just kind of group those together on one side and you have one big plus c. That's just a constant, so it doesn't matter if you just leave it off one side. I usually keep it on the right side. Now the point is to solve for y, because when we find the general solution, the idea is to solve this equation for y. So I'm going to use my definition here of ln and say, well, e to the 2x plus c is equal to absolute value of y. So absolute value of y is equal to e to the 2x plus c. And I'm going to use a little property of exponents and write this as e to the e to the 2x times e to the c. Now e to the c is just a number, because e is a number and that c is just a constant which will be determined based on an initial condition. So you can call that a new variable if you want. I know it seems a lot of my students get uncomfortable with this idea, but it really is fine, because all these constants are just yet to be determined anyway. So we can kind of lump them in and call them one big constant until we actually do find what they should be at a particular time. So the point is that becomes a to the 2x. That's the absolute value of y. And even here, if I have the absolute value of something, so like the absolute value of x equals 2 means that x equals plus or minus 2, I can say that y equals plus or minus a, e to the 2x, but the plus or minus can just be absorbed by the a, because again, that'll all be determined once we plug in an initial condition. So this is a legitimate answer to the differential equation. This is the general solution. All right, that's the general solution. If I wanted it to be a particular solution, I would have to give you an initial condition. I would have to say something like, this function, find the solution to this differential equation such that this function goes through the point, let's just say 0, 1. So let's say I had an initial condition. Let's say I said y of 0 equals 1. That doesn't need to be in parentheses. Well, now what you can do is you just plug in, you plug in 0 for x and 1 for y, and you solve for a. So when when x is 0, that's a e to the 2 times 0 equals, when y would be 1. Now e to the 2 times 0 is just e to the 0, which is 1, so that implies that a is 1. Which means that y equals 1 e to the 2x, this would be the particular solution. All right. So the big idea here is that, so there's the general solution and the particular solution. If you compare these to your actual slope field, what we basically said here is that, y equals e to the 2x is a function that it's an exponential, and it would go through the point 0, 1, because that was our initial condition. So it's going to go through that point up here, and it's going to look something like this. Right? Now if I had changed the initial condition, let's say I wanted to go through the point 1, 1, then that solution would probably look like this black line. It's going to go through 1, 1, and it's going to look like that. And on the other hand, if I made the initial condition that it goes through the point 0, -1, it would look like this guy in purple. So you can see that a slope field gives you the entire family of solutions, and you only lock in one of them if you're given an initial condition. Okay, so in future videos, what I want to do is a few more examples of this, because I think this technique, in particular the separation of variables technique, which we've just applied here, can confuse some students. So I'm going to do a couple more examples, but in the meantime, just hopefully you get the big picture here involving what it means to solve a differential equation, what the slope field represents, and the difference between a general and a particular solution. I just wanted to graph a few of the particular solutions that would go with this general solution. So you can see that they're all sort of taking the shape that is indicated by our slope field. And depending on whether your a value is positive or negative, that will determine the direction it actually goes in. The other thing is you'll notice that when a is 0, you get that horizontal line at the x-axis, which is the x-axis. And we found that, I mean, that's indicated clearly on our slope field, so that's kind of this degenerate case. Here, I'm going to just show you on Desmos an animation which just shows how the functions vary as your a varies. So I'm going to press play here, and you can just see that as a changes, our function's changing, and what you're seeing here is just a transition from each each member of the family in this solution to the differential equation is just kind of morphing into another version or another member of the family, I guess. And depending on whether a is negative or positive, it will take on a different shape.